Hello! It is time to jump to section 11.6. It's a beautiful sunny day here, so let's just dive right in. So we need some new vocab for 11.6, and we are jumping to 11.6 over 11.5. I think it just makes much more sense to do it that way. We'll see why in a little bit. But let's remember what we have been doing, okay? So what have we been talking about? Whether a series, right, that has this notation, which just means a sum of infinitely many numbers, and these are all the numbers, right? Whether that converges, adds to something finite, or diverges, right? Doesn't, right? Okay? So, let's again recall what that means. So, again, recall. Oh, I don't like this one, it doesn't write that well. Whoops. Let's recall that we have the sum n equals 1 to infinity of a sub n. What does that mean? It just means a1 plus a2 plus a3 on and on and on forever, right? Okay. So here, right, what we've been talking about is that these little numbers, right, these a sub i's, right, okay, each one of these numbers, they could be positive or negative, right? They could be positive or negative. Okay? But two of our methods required them to be positive. When we were doing the integral test or the limit comparison, several of our methods, limit comparison test or comparison test, right? These guys needed positive terms, right? And so those tests don't work if any one of these guys is a negative number. So that seems pretty limiting, right? The only time we can deal with allowing any one of these guys to be a negative number is if we had a geometric series or we had a telescoping series. And that's pretty limiting, right? So our goal then is to be like, well, can we come up with something more robust, right? Something that's going to make our life a little simpler and maybe not even have to worry about negative terms, okay? Because we got a bunch of tests that work for positive terms, yeah? Okay, so that's kind of the thought process. So the difficulty with negative terms leads us to wonder, right? That's what math is all about. Leads us to wonder, right? What if I only had positive terms, right? Wouldn't that be a nice world to live in? Yeah? Okay, nothing but positivity, yeah? Okay, so, well, we can do that in math, right? Well, what if we consider summing, right? So we're still going to add up a bunch of stuff, but we just want everything to be positive. Do we have a way of making everything positive? Yeah, good. What if we just added up the absolute values of everything, right? If we add up the absolute values instead of adding up the actual numbers. Now, they're going to be two totally different sums, right? But this one is guaranteed to have all positive terms, right? Because what does this notation mean? It means sum the absolute values of the a sub n's. So absolute value of a1 plus absolute value of a2 plus absolute value of a3, on and on forever, right? So we don't care whether a1, a2, a3, or any a sub I is negative. Summing the absolute value will make it positive. Yeah? Make sense? Okay, good. Awesome. Now again, they're two totally different sums, right? So we're not going to be asking, what is the value of the sum, right? We're just trying to determine whether it converges or diverges. So is there a relationship between these two guys, right? What do you think? You make a wild guess, and then we'll see in just a little bit if you're right, okay? All right, so that's kind of where we are. That's where this idea comes from. Notice that's also very different than taking the absolute value of a sum, right? If we did the absolute value of the sum, we'd add everything up, positive and negative, and then take the absolute value of the final result. That would be another totally different thing. Does that make sense? So again, your notation matters, right? Okay, so let's talk about this. So this is we call this the series of absolute values. Right? Series means sum, right? Sum the absolute values, right? Okay, good. Alrighty, so this is our concept. Let's see what we can do with this. So because we have this new idea, this series of absolute values, we need some new vocab. Yeah, just gonna double check the camera's on. I'm gun shy now. All right, we're good. Okay, so let's get some terminology. Yeah, all right. Oh, and before I completely erase this, right? What we've been talking about is summing infinitely many numbers. What we're leading to is summing infinitely many functions. That's where we're going to end, right? Okay, that's where this class is going to end. Not today, but that's where Math 236 will end. Summing infinitely many functions. So we're building our toolbox with numbers, right? So that we can then transition to variables. Okay, all right. So here we go. Let's talk about this concept. So let's get some terminology. So, let's first make a definition. Let me just make sure I save these all. So we say that a series, right? Sum of n, that's our guy. That's who we're trying to figure out converges or diverges. But we say that series is absolutely convergent, like absolutely convergent, right? What do you think that means? Right? Or we can also say, or converges absolutely. Same thing. This depends on what word you want first. It's absolute. No question. It's absolute, right? What do you think that means? We say that a series is absolutely convergent if and only if what? You got it. The sum of its absolute values converges. Right? That's awesome, right? Absolutely convergent. Yeah? Okay? So, why is that great? Because if we look at the sum of the absolute values, we got lots of tests that work. Yeah? Because everything's positive. We good? We all together here? All right. Okay. So, that's our definition of absolute convergence, right? If and only if means we go this way. It's a definition, right? This means this and that means that. If a sum of the absolute values converges, then a series is absolutely convergent as well, right? Definition. These two things are equivalent. Okay, so what if you're not absolutely convergent? What are you? Okay, let's talk about that. Now there's a new middle ground. It's not just, oh, if you're not absolutely convergent, you're divergent, right? Before it was if you're convergent, if you're not convergent, you're divergent, yeah? But we now have this new middle ground. Okay, so what is this middle ground? We say that a series, sum an, right? The an's going to be positive or negative, right? That's the whole deal. We say that that is conditionally convergent. Conditionally convergent, or, you guys tell me, or it converges conditionally. I don't really like this terminology. We'll talk about why not in just a minute, but this is the terminology we have, and so we have to go with it. Or converges conditionally. Okay? What does that mean, right? We need to know what these things mean when we're talking about them. So what does that mean? Conditionally convergent. So we say that if and only if, so here's what it means, right? Okay? This is what it means. First of all, what it means is the series itself converges. Whoops. Okay, so if I add up these terms, some are positive, some are negative, right? Whatever, that sum ends up being some finite number, okay? So conditional convergence is convergence, right? So don't, worry about that, okay? So I don't like the wording because it seems like, it's only convergent under some condition. But anyway, we'll talk more about that later. So conditional convergence is convergence, right? But there's something else, right? So if that guy converges, but it doesn't converge absolutely. If we change all the positive things to negatives, then that guy diverges. Okay? Does that make sense? Okay? No, that doesn't make any sense. What did I just say? When we change all the negative things to positive, right? Then that guy diverges, right? You change every negative guy here to a positive, add that all up, that diverges. So what does it mean to converge conditionally? You converge, but you don't converge absolutely, right? So what does this mean? I.e. convergence, but not absolutely convergent, right? That's what conditional convergence is. Convergent. Yeah? Okay? All right. And so if you're neither absolutely convergent or conditionally convergent, then you diverge. Yeah? Okay. All right. So let's talk about this idea. Okay? Makes sense? Are we good? Yeah? We okay? Okay, so this makes a lot of sense to us, right? But we still want to come up with a theorem and prove some things. It makes a lot of sense that this concept could help us figure out what's happening with the series. All right, you got this? I'm going to erase, yeah? We usually abbreviate conditional convergence. I'm going to use a different color. Conditional convergence, conditionally convergent, right? And absolute convergence is absolute convergence, just to not have to write that all out all the time, right? So a series converges absolutely if and only if the series of absolute values converges. The series converges conditionally if you have convergence for the series, but the series of absolute value doesn't converge, right? It diverges, yeah? Okay? So let's write down a theorem. We're going to do an example too, but we got to get our theorem first so that we even know why we're doing examples, right? Okay? You got to have terminology, you got to have definitions so you know what these things mean. All right. Anytime we write down some definitions, that leads us to a theorem that allows us to make our life easier, right? Okay, so what's the theorem? Theorem may make sense to you. It says if a series converges absolutely, then, right, the series converges. What? It may seem obvious, right, to you, but nothing is necessarily that obvious, and especially the most obvious things oftentimes are the things that are most tricky to show. So let's see what this actually, let's think about this again. What? What did that say? So what else does this say? Let's write it differently, right? If, what is this the same as? The sum of the absolute values converges, right? If the series of the absolute values converges, that's the same as saying AN converges absolutely by our previous definition, right? Okay? Well, that series converges absolutely. Its series of absolute value converges. So if that converges, then this converges. Well, that makes a lot of sense, right? Okay? That makes a lot of sense. We're adding up terms that are bigger, right? If you take the absolute value of everything, right, then everything over here is going to be bigger than everything over here. And so it makes sense that if the series of bigger things converges, then the series of smaller things would converge. Yeah? Does that make sense? What does that sound like to you? What are we going to use to prove this? Let's see if you're right. Okay. Yeah, we're going to prove it, right? Just so that you make sure you understand, because this is the thing that's going to like fuel most of what we do from now on. So we want to know, we want to see why this is true. Okay. How would we prove this, right? What do we know? Okay. So what do we know? Okay. So we say let the series of absolute values converge. Right? Yeah? That's the only thing we know, right? That converges. What do we have to end up with? Well, that guy converges. Okay? Well, we got nothing. We got very little. Okay? We got very little to work with. So that's when you dig in your bag of tricks, right? Okay? So let's dig into a previous bag of tricks. We did this once before with something else that we proved. We need to come up with something about AN. We already kind of hinted at how you might prove this, right? We're comparing the size of this to the size of this, right? This is the bigger series. The bigger series converges and the smaller series converges, right? And so we want some inequalities on AN, yeah? Well, and what is the other thing that we have? Absolute value of AN. So what's the relationship between AN and the absolute value of AN? Which one's bigger or equal to, right? Good, right? That's always true, right? Yeah, that's always true, yeah? All right, nice. This guy could be negative, yeah? But we need something on this side also, right? Because in order to use the comparison theorem, right? I knew you were thinking that. This side has to be positive. So right now, right, the ANs, these guys could be negative, right? That's the whole point. That's why we're coming up with something. So you can't just say, oh, that's positive. So we need something that it's definitely bigger than. What is that definitely bigger than? Anybody? Do you remember? Minus the absolute value of AN, right? If I take the negative of the absolute value, then that's always going to be less than or equal to AN, right? Okay, check it with some numbers if you need to. But this is a true inequality that holds no matter what, right? A number is always between its absolute value and the negative of its absolute value. All right, so we're in better shape now. We at least have an inequality, but we can't use this inequality for the comparison theorem. Why? Because this piece is negative, right? Comparison theorem requires all positive, everything has to be positive in the inequality. So how are we going to change this inequality into something where we have, stuff is bigger than 0? Well, you puzzle, you think about things for a long time, but we don't have time for all of that. So what do we do, right? If I want this to be bigger than 0, then I'm just going to add the absolute value of AN across the inequality, right? That makes sense, yeah? Okay? Are we all good here, right? So that's where the idea comes from. So if I do this plus this, what do I get? Good. 0 is less than or equal to what? Well, I have a sub n plus the absolute value of a sub n, right? And that's less than or equal to what absolute value of an plus absolute value of an is how many? Good. 2 absolute value of an's, right? So this is the inequality. So we started with this, right? An algebraic truth. And then we got down to this inequality, which is our important one. Now we're close, but we aren't there. So let's talk about what we got so far. All right, so now what do we have? Okay, so because of this inequality, right, then what do we know? We know that the sum of the absolute value of AN converges, right? That was our given, yeah? We know that converges. And 2 is a good constant, right? Therefore, by the, constant multiple rule, good, that was on the test, constant multiple rule for series, right? Then what do I know? I know that the sum of 2 times the absolute value of n converges, right? So that's a constant, so that guy's convergent, a constant times that guy is convergent, right? So I know that the series, this bigger series, converges, right? Now, what does the comparison theorem then tell me? Well, so the comparison theorem says this series in the middle converges. So we're not quite at what we want, right? Okay? I can use the comparison theorem now because everything's positive, right? So the comparison theorem says the sum of AN plus the absolute value of AN also converges. But that's not quite what we want. Right? What do we need to conclude? We need to conclude, right, this is a, right, that's all in parentheses. We need to conclude the sum of AN converges, not AN plus the absolute value of AN. So while I'm erasing, maybe you can think about how we're going to get from here to there. Creating some more space, right? So here we go. You ready? Do you have the idea? Okay. But what do we know? Well, we got a couple more rules of algebra, right? But by our algebra of series rules, which we've proved, right? We know what? Well, let's see. We've got the sum of AN, right? That's kind of what we want, okay? We want to be able to say that that converges, right? But we need to somehow use this, right? And so, again, by kind of knowing where to go and thinking cleverly, I need to write AN with an absolute value of AN, right? So I can say that that's the same as the sum of AN plus, well, I can't just add absolute value of AN, right? What is one of my favorite tricks as a mathematician? If I'm adding, good, add 0, right? There you are, right? I can say AN is the absolute value of N minus the absolute value of AN, right? So those two things are absolutely equivalent because all I did was add 0, right? Yeah, fantastic. Awesome. And so now what? Now I'm just going to regroup, right? So I'm going to group these guys together and that guy off by himself. So I'm going to say, okay, well, that's the sum of AN plus the absolute value of AN, right? Minus the whole thing, minus the absolute value of AN, right? Didn't do really anything more than just basically say, I'm going to stick parentheses in there, yeah? Which is totally legit. Okay, so now what? Well, what do I have here? I've got a difference. What do I know? Do I have a rule of algebra for series that says the sum of a difference of convergent series is the difference of the sums? Absolutely. And does this series converge? It sure does, right? We grabbed that from the comparison test. And does this series converge? It sure does. That was our hypothesis. And so this by the difference of series, right? The algebra rule for difference of series, the difference of a series is a series of the differences. We have that the sum of an, that this whole thing is this, right, minus that series, right? The sum applied to each one separately, and we know this guy converges, and this guy converges, and we know that the difference of convergent series converges, right? Therefore, the whole thing converges. But what was that equivalent to? Our guy an, right? So therefore, this guy converges. Woohoo! Yeah, right? Okay? Super fun using our various algebra of series ideas. All right, so let's recap this piece. What does this rule say? One more time, the most simple way to say it. This theorem is awesome because that's really what we're going to be relying on from now on, right? What does this theorem say? It says, what's the simplest, shortest way to write this? What does it mean for a series to be absolutely convergent? The sum of the absolute values of an converges implies what? The sum of an converges without the absolute values. So let's go look at an example now. Now that we understand why this guy works and we saw all this beautiful stuff come together from the previous things that we've had to develop in order to see why it works, right? That's where the magic happens. Okay. Alrighty. We're several pages away. Okay, so here we go. Let's look at an example. This is section 11.6, exercise number 4. Let's see how this all applies. So here is the sum, n equals 1 to infinity, of minus 1 to the n divided by n cubed plus 1. Okay? And the question is, does this converge or diverge? Okay? Now, notice, right, what is this series? Whoops, let me just put that over here. Converge or diverge? That's the question, right? So let's just write out a couple of terms of this series just to make sure, like, we're remembering, like, when we write this thing down, what does it really mean, right? So when n is 1, what do I have? On top, I've got a negative 1, right? And on bottom, what do I have? 1 cubed is 1 plus 1 is 2. Yeah? Okay? And then we add, when n is 2, negative 1 squared is 1 divided by 2 cubed, good, 8 plus 1, 9. Yeah? Let's do one more, right? When n is 3, what do I get? Plus a negative 1, right? And we'll just do it like that at first. Plus a negative 1, yeah? Divided by 3 cubed. Good. 27, yeah. Plus 1 is 28. Are we good? Right? Okay. All right. And so then what's, it just keeps on going, right? Now we could rewrite this as minus a half plus a ninth minus 1 over 28 plus, right? So this is also called an alternating series, okay? This is an alternating series because it alternates sign, yeah? Let me just say, section 11.5 is about alternating series, okay? There is a test for alternating series. We're only going to use it when we need it. We're not going to use it here. We are not going to need it. You're going to see why, okay? Series that have negative terms aren't always alternating. They're special. You could have like negative, 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 positive, positive, negative, positive, negative, positive, negative, negative, right? Okay, so alternating has a specific form. But, like I said, we're not going to use 11.5 alternating series test unless we have to. So here's the series that we're trying to decide, does this converge or diverge, right? it's got negative terms, so you can't use any of the methods that we had before. You can't do limit comparison test with this, right? Because this has negative terms. Limit comparison test proof relied on the terms being positive. So we got nothing, right? We just have nothing except for our new result, right? Which says, okay, well, check for absolute convergence. Right? Just check for absolute convergence. Basically, ignore all the negatives and make them positive. Right? Okay? And so, if we write it out specifically, then what would we be looking for? Maybe I'll do this one in blue. So, we're really asking, does the sum n equals 1 to infinity of the absolute value of negative 1 to the n over n cubed plus 1, does that converge? Maybe we'll just say it like this. Consider this. Consider instead the series of the absolute values and ask, does that converge or diverge? Right? Now let's write out that just again to see what that would be. Now notice, right? Okay, so here, what are we going to have? We already wrote out these terms. What is the series of absolute values just going to do? It's going to turn everything negative positive. So what is the series going to be? Yeah, 1/2 plus 1/9 plus 1/28 plus da 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 da, right? Does that make sense? Okay? Now clearly what this adds up to and what this adds up to are two totally different things, right? So testing for absolute convergence isn't going to tell you anything but maybe an upper bound on the sum of the original guy that you actually want, right? Does that make sense? Okay? But it is going to tell you convergence, right? If this guy converges, then adding up the guy with some smaller terms is going to converge. Yeah? That's our deal. So now, does this like negative 1 to the n thing have to be like, ooh, scary to us, right, in this absolute value, right? No. What is this series, right? The beautiful thing is this guy's always positive, n cubed plus 1, right? N is bigger than or equal to 1. And so really, your absolute value is just the absolute value of negative 1 to the n. Well, negative 1 to the n, we know, is just something that alternates back and forth between plus or minus 1, right? Okay? So you don't have to get all crazy with absolute values. Ignore a variety of things that your book does with that. What are we really interested in, right? The question is, does the sum n equals 1 to infinity of 1 over n cubed plus 1 converge or diverge? That's the question, right? This is that. When I take the absolute value, all I'm really going to get is an absolute value on the top, right? And then the absolute value of negative 1 to any power is always 1. All right? And so we're just looking at this guy. Well, this guy, you know, could have been on your test, right? This is what, right? What do we do? This is limit comparison test, right? What would I do? I think about 1 over n cubed plus 1. And that is a little bit like 1 over n cubed, right? For n getting huge. The highest power of n up here doesn't exist, 1. Down here it's n cubed. So this is my, let Bn be 1 over n cubed for my limit comparison test, right? And this guy is a p series with p equals, good, 3. What do I care about for a limit comparison test? I want p to be bigger than 1, strictly bigger than 1, and then I will get convergence. So here is a convergent p series because p is bigger than 1, right? 1 over n to the p. All right, I'm going to compare with that. So what do I do, right? How do I do limit comparison test? I take the limit as n goes to infinity of an over bn, right? So what is my an this time, right? I'm ignoring, I don't care at all about the original problem, which had negatives, right? I'm looking at this guy, so my an is 1 over n cubed plus 1, and what is my bn? 1 over n cubed, That's what I'm setting up for limit comparison test, right? Okay? So now what do? It's the limit as n goes to infinity. I just do the algebra. I'm going to erase this, right? Create space here to finish this guy up. Algebra fractions. What do I got? Good. That's the limit of n cubed over n cubed plus 1, right? You're going to have to be good at that because we're going to have a whole bunch of that coming, right? What is that limit? It's infinity over infinity. You can either do L'Hopital's rule 3 times, right? Or you can use our method where we divide by the highest power of n in the denominator, which is n cubed. When I divide the numerator by n cubed, what do I get? Good, 1. See, we're fast at this now. When I divide this guy by n cubed, what do I get? 1. And this guy I get 1 over n cubed, right? You gotta justify, show you know what you're doing. Alrighty, then what? I'm taking a limit as n goes to infinity. I've got these beautiful constants right here. The only thing with an n in it is now this guy, and therefore 1 over n cubed as n grows large. Good, that goes to 0. 1 over something getting huge goes to 0, so what is my limit? 1 over 1 plus 0, which is 1. What do I care about in the limit comparison test? I care that this is positive, right? Or not 0, either one, okay? It's fine, as long as you say that, you show that you understand the limit comparison test, and therefore, what do I know, right? I know both series do what? Converge, because I compared with the convergent p series, right? Therefore, both series converge, right? So what did we just now show? We showed that if we ignore the negatives and think about the positive guy, this guy converges. So since that converges, the series of absolute value converge. What do we say up here? Therefore, since the series of absolute values converges, our series converges, right? We're using our theorem we just proved. Okay? Or what do we say? Much shorter, which is what we're going to be saying, right? Our series converges. I'm not even going to write the series just because I don't want you. So we have our original problem for number 4. What do we have? Absolute convergence. That's what we got here, okay? So it's not really even converge or diverge anymore. If it's converge, it's absolute convergence or conditional convergence, right? That's the question, yeah? So now we've got 2 things to do, and absolute convergence is the one we hope for, because absolute convergence means we're done, right? If it had turned out that the series of absolute values diverged, we would have known nothing about this series, right? If the series summing the bigger numbers diverged, that would tell us nothing about this thing. Then we would need another test to see if our series was conditionally convergent. Remember, what did conditional convergence mean? The series converges, but the series of absolute values doesn't, right? Okay? We weren't in that case. We're always hoping for absolute convergence because that means we have less work, right? Okay? Does that make sense? Okay. When we don't have absolute convergence, then what we're going to see in a future lecture is for conditional convergence, there's only one option, and you've got to hope you have an alternating series and then apply a new test called the alternating series test, which we're not going to learn just yet. Okay? All right. So, woohoo! We're good. All right, we're going to now talk about another new test. So let me just maybe kind of, does this make sense? Are we all good here? Do we understand? Okay. So this guy converges absolutely. That is our final conclusion of this problem. We have nothing more to do for this problem, okay? Our new goal, right, is new tests. New tests for absolute convergence. New tests for absolute convergence. That's the rest of section 11.6. And actually what I think I'm going to do is maybe end this video here and then do another one where we start with those new tests. Okay, so I'm going to post 2 videos for our final lectures of this week. And one thing to keep in mind, our new tests that are coming are going to be the guys that are going to be super awesome, and ones we're going to keep using consistently. I'll give you a hint. They're called the ratio test and the root test. These guys are going to get used consistently throughout the rest of the semester with when we move from adding numbers to adding functions, okay? But you can't ignore or forget the tests that we had before. So in particular, the ratio test and the root test would have not allowed us to answer this problem that we just did, 11.6 number 4. So one of the things we're going to see about these 2 tests is there are cases when they fail and they tell you nothing. So you've done it and it would have told you nothing. And so for this one, we tested for absolute convergence and we used the limit comparison test, right? So this guy, we used the limit comparison test to test the series of absolute values, which was this guy, right? Basically change the positives and negatives. And the limit comparison test immediately told us that this guy converged and we got, therefore, absolute convergence, right? If we had used either of these 2 tests, they would have been in their 3rd case, which is the inconclusive case where you would have known nothing. And so one of the other things we're going to want to develop as we're moving through is when do we use the ratio test and root test? They're not always the go-tos because they can fail. And then you would have to do something else, like use the limit comparison test. So we'll be looking for that too. All right, I will be back soon, and I hope you're having a great day.